So without wasting much of our time, I would like to call Mr. Matthew Ekum for continuation of our R programming we are doing today, predictive modeling, and let's welcome him. Thank you. Over to you, sir.
Good evening. Good evening.
Good evening. We can hear you.
Can you hear me?
Yeah,
okay.
We can hear you.
Yes,
Go ahead.
Okay, want to look at predictive modeling today, but there are some other things we'll look at before the predictive modeling. We are not going to machine learning per se, but what you get today is just an idea of what machine learning is all about. But actually titled with predictive modeling, so that we know that we actually want to predict some variables. The content, we look at real life problem using Uber data set. The Uber data set is available on Cargo. We have Arrow code for it, we have Python code for it, but the code I'm using today, I just try to use my own code so that it can suit what I want to teach this evening or what you want to learn this evening. We'll look at how to import data from CSV file. We can't be tired of that. Exploratory data analysis, then checking and removing NA, then data frame and subsets. Data frame are same as tables. Then subsets out of the table, we want to get some subsets from the table. Then split data into test and print sets, and regression models, then model selection criteria. Just look at this quickly. Then we'll now go to the code, to the Arrow Studio itself. We look at how to import data from CSV file. This is not anymore new to us. If our data is saved in CSV file or in Excel, we can save it as CSV and import it to our environment. The process that you click on the file from the menu bar, you click on Save As from the drop-down menu, choose the location where you want to save the file, name the file in the file name, and click the Save As type. Then in the Save As type, it's a drop-down button, select the CSV command delimited, and save, and click on Save. You have saved your data in form of CSV, even if it's in Excel, SLS before. It is now in form of CSV. Then the next thing we want to look at is the Uber data set. Though the Uber data set that will be downloaded for us is already saved as a CSV. So let me quickly look at the Uber data set. See, ride sharing is a service that arranges transportation on short notice. It is a very volatile market, and its demand fluctuates widely with time, place, weather, local events, etc. The key to being successful in this business is to be able to dictate patterns in these fluctuations and cater to the demand at any given time. So the objective is Uber Technologies is an American multinational transportation network company based in San Francisco and has operations in over 785 metropolitan areas with over 110 million users worldwide. As a new hired data scientist in Uber's New York office, you have been given the task of extracting actionable insight from data that will help in the growth of the business. So let's look at the Uber data set itself. The key questions are, what are the different variables that influence the number of pickups? Meaning that what we want to predict, our dependent variable here is the number of pickups, but there are other variables that we can use as independent variables or predictor variables that can actually predict the number of pickups per time. So which factors affect the number of pickups the most? Among these predictors, which one do we think affect the number of pickup the most? What could be the possible reason for that? Then what are your recommendations to Uber management to capitalize on fluctuating demand? So from the first two, we can then make our own conclusion as managers based on what we have derived or what the model has given to us. Then we have the data description. In the data set, we have the pickup date. That is the date and time of the pickup. We have the date, then we have the time in hours and in minutes that the pickup was, the date for the pickup. Then we have the borough. Borough is NYC borough. We have different, maybe like we have localities, different localities in that particular variable called borough, which are locations or localities. So it's not a numeric value. We talk of local places, locations. Then we have the pickup itself. That is the number of pickups for the period, and it's measured hourly, maybe 2 hours, 5 hours, and so on. Then we have the SPD, which is the wind speed in miles per hour. We have variables VSB, visibility in miles to the nearest tenth. Then we have the temperature in Fahrenheit, measured in Fahrenheit. We have the dew point, also measured in Fahrenheit. We have the sea level pressure. We have 1 hour liquid precipitation. We have 6 hour liquid precipitation and 24-hour liquid precipitation. Then we have the snow depth in inches. Snow depth measured in inches. We have the holiday, if the day is holiday or not holiday. Definitely days that are not holiday will be more than the days that we have holidays. But we want to look at all these situations. Then using CSV method, this is how we can read the data set. As I said earlier, the data set and the script should be in the same folder, so that when you are running the script, when you are running the command, you can easily attach the data set into the other environments without having issues. Otherwise, you have to look for the path where the data is and bring it to the other environment. So we have the syntax, we have the arguments. We have seen this before over and over. So we should just learn this, and we know it's at least by now, most of us should know how to write this read.csv code, even without copying and pasting. I believe so, or I hope so. Then want to look at exploratory data analysis. Exploratory data analysis use the hidden features in a data set. If you are just looking at your data set from the table, I tell you there are some things from that table, especially when we have a large data set like the one we have today. There are some things on that table that you can never be revealed to you. But if you use EDA, there are some patterns that will be revealed to you that will make you to quickly know that, oh, this data set has missing value. This data set has this data set has outliers. This data set, you can easily get that. And EDA involves exploring a data set in 3 ways. One, identify missing values. That is one of the processes to do when you are doing your EDA. You make sure that you clean your data. And one of the ways you clean your data is to make sure that the NAs are removed. NAs are different from 0. 0 means the value, there is a value there, but it's 0. But NA means it is empty. So we should be able to differentiate NA, which is the missing value, from when you have 0. Just like a student did not come to class, and therefore the student does not have test, meaning that that's a missing value. But when the student score 0, it means that the student actually attended the test, but scored 0. So there are 2 different things. If you add 0 plus 2, it will give you 2. But if you have add NA plus 2, it won't give you anything. Then summarizing a data set using descriptive statistics, like use of summary, it will give you your 5 norms, 5 norms plus mean. The 5 norms in statistics are the minimum value, the first quartile, the median, the third quartile, and the maximum value. Then the mean is also added to it when you use your summarize, when you use your summary. But when you use 5 norm, to just give those 5 values. But when you use summary, it will include mean to make it see. Then visualizing the data set using charts. You can use chart, graphs, plot, different plots to visualize data sets. So all these come under your ED. I call them preliminary analysis. Analysis you have to carry out to see the nature of your data, especially for the dependent variable, which is to be predicted. Then let's look at checking and removing NA. In our missing values are represented by the symbol NA, not available. Impossible values, e.g., when divided by 0, that we call infinity, or undefined, are represented by the symbol NaN, not a number. When you have 2 divided by 0, what it will return is not a number. And sometimes it might be 2 divided by a value very close to 0, it might still bring NaN, meaning the divisor is a very small number that is almost close to 0. So you can still bring NaN. How do we know if there is NaN in a data set? Once you have called up the data set into R, the next thing you do is to write this code, this particular code. Let me select it. Any is NA data. It will return true or false that yes, there is NA in the data or there is no NA in the data. Once it returns true, then you go ahead with other analysis. But once it returns false, once it returns false, you go ahead with other analysis. But once it returns true, it means that there is NA, there are missing values in the data set. The next thing you want to do is you want to remove the missing value. So use this code, NA.omit.
You have it tomorrow.
You say?
Go ahead, sorry,
the volume is low, Abby. Is the volume low?
Go ahead. You can increase your volume.
Okay, I thought somebody is talking at the background. That's why.
Yeah.
Okay, let me continue. So NA.omit, then you put the data. I mean all the data sets with all the variables. That is the data you actually called from the CSV file. And you name it. The data here is the name that you have given to him. You can call it data or what, data 1 or whatever name you wish to call it. What you just do is NA.omit. It will omit all the rows with NA. If there is NA in a particular variable, it means that all that row will be what? Omitted. But the danger there is that if most of the values are NA, then it will reduce your data set. Though many people have proposed many ways of replacing the missing value with different, some will say replace with me. Some have a way of calculating the missing value to replace it instead of omitting it. But that is not the teaching for today. What you want to learn today is how to completely omit it and reduce the data set to a set that does not have NA at all. Then, as I said, NA.omit, we remove the NA from the data set. Then, data frame and subsets. A data frame is a table or a 2-dimensional array-like structure in which each column contains values of one variable, and each row contains one set of values from each column. So it's 2-dimensional, but all the columns have columns name. Then the rows are the cases or the observations. So a data frame is nothing but a table. So following are the characteristics of data frame. The column name should be non-empty. That is, every column must have heading. The row names should be unique. All the rows just, it is, we have the index that shows one row different from another row. Then we have the data stored in a data frame. Can be of numeric, it can be a factor or character type. Unlike matrices, that all the rows and columns must be of the same type. Each column should contain same number of data items, meaning that column 1, if the column 1 has 20 observations, column 2 should also have 20 observations, column 3 should also have 20 observations, and so on. Then the data frame, syntax from data frame, if you have variables that you want to put in data frame, maybe you have different variables, you just want to combine them and put them in data frame, you use, pardon me, this is not capital letter D, it should be small letter D, data dot frame. Then the variable names that you want to, just like cbind. Cbind is different from data frame, but they look alike. Then we have describe data frame table. If you want to describe a data frame or a data in a table, you use the str data. This code will tell you everything about the data frame or everything about the table. To tell you the number of observations, the number of columns or variables. It will tell you each of the variables, if they are numeric, if they are character, whatever they are, it will show it to you. Then the next thing we also look at the scatter plot of variables in a matrix. We use pairs. If you have 10 variables and you do pairs data, data here is the name given to that data, it will do a correlation matrix showing the scatter plots of all the variables. This will help you to know the variables that are correlated and the ones that are not correlated. Then the subset is used to get values out of the tables. For example, you have your table and you want to extract gender. You want to use gender as the column name. The arrow one here shows that, okay, if the gender is a male, bring out from the data frame, this is the name of your data frame, subset, this is the name of your data frame. Then the column name, the name of column name. If it is gender, you put gender. Where gender is equals to male, this will generate a subset from that table that comprises male only and with all their attributes. So that's what these subsets will do. We actually use this subset, all those locations under borrow, we use this subset to bring them out. Then another good thing we do in, that's why I said machine learning is part of it, because in statistics generally, when you want to predict, most cases, we don't need to necessarily divide the data into training set and testing set. So the idea of dividing data into training sets and testing set is actually from machine learning, which will make you to have the input, you train the input and the output to get the program. Unlike in statistics, where you put the input and the program to get the output. So in this case, both the input and the data and the output are trained together to get the program. So we now use some percentage to validate, like what you have here, the syntax. The syntax we have here, we say sample.split. That is the way we write in our sample.split is the keyword. Then we put the y variable, that is the dependent variable. We put the split ratio 0.7 group. No, this 0.7 here is saying that we divide the data into 0.7 and 0.3, meaning 0.7 should be used for training data sets and the remaining 0.3 should be used for testing in the model. It can be 0.8, you can make it 2/3, meaning that 2 out of the 3 should be for, 2/3 should be for the training, and 1/3 should be for testing. In most cases, some people use 0.8 and 0.2 or 0.7 and 0.3. depending on some people use 0.65 and 0.35, depending on what you want. So once you put 0.7 here, it knows that the other one is 0.3. So once you put sample dot split, so the Y is the vector of the data labels, and if there is only a few labels as expected, then relatively ratio of data in both subsets will be the same. So we split ratio. Splitting ratio is if this split ratio is between 0 and 1 and less than code, to be this. Then split ratio fraction of point from Y will be, when we get to the code, you understand what is here. What this place is just saying that if you run this code, it will return true or false. Then the true should be for the training, while the false should be for the testing. Like what I have here, let me quickly go to this place. Like what I have here, I say training sets. You can see the subset code here, S data, the sample split. This sample split here, if it returns true, then it should be for training sets. That means 70% should go for training sets, and the remaining 30% should come for test sets, which is false. We also use it in cluster analysis. Maybe you want to divide the cluster into two. You have 1 and 2. In this case, you have true and false. In case of this, because what it will return here, what this code will return is either true or false. So you split the data into 2, meaning that 70% of the data will be true, while the remaining 30% will be false. Then the model, as I earlier explained, I explained this regression model last week. We have the linear regression model where we use LM, and we just use one dependent and one independent variable. But in the case of a multiple linear regression, we have multiple independent variables, more than one independent variables. So in this case, we have K independent variables. The betas are those parameters we want to estimate. The Y is the dependent variable, as I said. The X are the independent variables. E is the error term. And the idea is to minimize the error term, which I explained. And the predicted Y for the simple linear model is this. Predicted Y for the multiple linear model is this. So once you have done this, we can do different model. I'm just using these two models as an example, the linear model and the multiple linear model. The multiple linear model we can have of different forms. Then we cannot compare the results. But if we go into machine learning proper, we look at other models that we can use. But this is just to help us to understand that, okay, once we have our models, we can actually compare the performance of the model. And these are some of the model selection criteria. That is the MUIS and CP. We use 1/n. N is the number of observations. Then the residual sums of square plus 2D sigma. Sigma is the standard error for the model. The D is the number of predictors that are in the model. So we use this, we minimize this. Meaning that the one that has for AIC, we use this formula, and the one with the least AIC is the best. For Bayesian information criterion, this is the formula that is used, and the one with the least is also the best. That's why they are putting minimize, minimize. But for adjusted R square, that is this, the one with the maximum is the best. So for CP, for AIC, for BIC, the one with the minimum value are the best. But for R square and adjusted R square, we look at the one with the maximum value. So these are some of the definitions we have given to it. So each of these statistics adds a penalty to the training the residual sum of square in order to adjust just for 5. So clearly, nothing increases as the number of predictors in the model increases. So what if you look at all the number of parameters, if the model will be best or not. So that's why that number of predictors are always there. And what you are always measuring is the residual sum of square, which is the difference between the actual value and the predicted value squared. Then with that, you can get all this formula. Once you know the formula, you can get them. And sometimes you can just, some of them have like AIC, you can easily get your AIC from the data sets and so on. And there is always a relationship between the AIC and the BIC. But let's just leave that for now. And thank you for listening. So by now, I expect everyone to must have downloaded their scripts and the data sets on their system. As I start to share the new screen. Let's share the new screen. Let me share the new screen.
Go ahead.
Okay. Okay. Can you see my scripts?
Yes.
Okay. The first line there that you can see there, I've already opened my script, so you can all open your own. The procedure of opening is still the same. If you run this first line, it will remove everything on this console. We'll be seeing everything in the console, but anything you run again will not make sense because I have removed all the variables, all the objects from the console. So the next line there is, I will say, this is a comment, we should install this library. Some of us would have started installing the library by now. If you run them, all this library will be what? Be installed. So by now, we should know how to install library. Maybe we should start installing the libraries now. Let me just give us like 2 minutes for some of us to install our libraries because it's very much important. Those of you that have not opened it, let's download this, open the scripts, make sure the data is also downloaded, put the data and the scripts inside the same folder so that it will be easy for us. So let me just hold on a bit for us to download.
Don't only hold on. Yes, maybe you should also show us. I know you have already downloaded it. Maybe you should also show
Maybe
us
some of
where
us
to
should
go.
be showing because some of these libraries will be needed, or even if the libraries are not needed immediately, at least let us make sure that we have our scripts open and our data set is somewhere inside the same folder where we have the script. So as I'm running it, I want us to be running it so that I will not go far before someone will now open it. I want at least many people to open their system so that they can have this, open their RStudio, open the scripts, so that as you are running it, we are running it together.
My request is that kindly show us how to do the installation from this package you have seen here. So
Okay.
I know you have done it already, so that people can, those that are not in tune
Okay,
with
let's
that.
start with the first one, the DPLYR. What you do, just know the name of the package. If you know the name of the package, maybe I should copy it. Know the name of the package, come to packages. there is this environment has 4 compartments. The lower left and lower right compartments has packages. Click on the packages and click on install. Then you enter let me do as if I'm just entering. Okay. As if I'm typing, you can see the package. The name of the package is already there. You just click the package and click on install. When you do this, once you complete the installation, if you see my, I don't need to install it again because I've installed them. If you see my cursor here, it's blinking. At that point, you'll be showing that yes, it has finished installing, meaning that you can do other things. So let's do the installation for now. So let's install the packages so that you can flow, because I might not have time to start explaining where we need each of the package. That's why the packages are always at the top. So once you run all the packages, all the libraries, installing the package is different from running the libraries. After installing the package, you still have to call it, just the way I've called it, library this, library that, library that. You must call the library before you can use it. So after the installation, you can now run the library. So since all the codes are there, the major thing you just need to do is to install the packages. That is the major thing. Then you now run let me run mine and see. Yes, that one is running. ggplot, cat tools, and the code gram, the carrot, and the VIP. Yes. So they are all running well. Then I want to bring my data set now. The name of my data set is uber_data.csv. uber_data.csv. And I want to save it. I want to put it inside data 1. So if I run this code, I have achieved that. You can see there's no error showing. But if you have error showing, meaning that you have not set your directory. So for you to set your directory, I still have to go back there because you have to know this. The default directory, as I earlier said, is your document, my document. But if you have a folder, it means that you have to set your directory to that folder. Let me do it again. You go to section, then go to set working directory, choose directory. Then you click on, my own is, okay, let me assume it's inside my documents. Look for where it is inside my document. It's in data analytics class. I click on open. Can you see that I've set my directory? So you can see I've done that. So attach data means I want the data to, it's not necessary, but it's always good to attach data to make sure that the data is there. The data will always be there until you run this first line. This first line remove. Once you run this first line, the data is gone. You have to, even all the libraries are gone, you have to run them again. Once you run that first line, I kept it there in case if you have done so many things, I want to clear everything from the memory, just run it, clear it, and start running everything again. So now.
Sorry, Ekon. Is it possible you open another script? Save it in your folder, the same folder.
Okay.
So that while you are using you keep original and you'll be using that one to do the work. So that some of us that we are following will be also be able to follow very well. So that it won't mess. Yes. Just like, no, it's okay like that. Probably first 10 line, 20 line, 30 line, and so on. Thank you, sir.
So let me open new script, new. I click on file, new file, then our scripts. I paste. Because if I
Exactly.
start typing all over, we might not be here today. So now at this point, let me clear everything I'm having here. If I run this, I have cleared everything. You can see the upper right here. Environment is empty. Look at this, the upper right part. Environment is empty, meaning that I have cleared everything, both variables, objects, anything has been cleared. Everything has been cleared here. So I can even this one, if I want to clear it, this console, the down part here where the command from, if I want to clear it, I'll just say Control L. Control L will clear everything you are seeing there.
Somebody is asking a question. Where did you clear?
I've done two clearing now. The first one, just see that
Number
first
2.
line. That first line, let me remove the arrow M there. Just click and run it. Once you run it, you have cleared everything. You have cleared everything. That's why you are seeing the upper right there showing environment is empty. You can see my cursor on this right hand. It's showing that this environment is empty. Both global and local environment empty. Then, if I want to now clear the console, as I said before, 2 keys, your Control key and L for lion. Just hold down the Control key and press L. If your cursor is blinking, if you have your cursor on your command prompt, it will clear everything that is there. You can see that everything here is cleared. You are seeing my screen. Everything down left is cleared without Control plus L. So I have to start calling the library one after the other again. I have to call the library one after the other. Then I have to load my data. I have to attach the data. So attaching the data, you see all the variables name. All the variable names are arranged alphabetically. You can see them. All the variables name are arranged alphabetically. So I have attached that. Then the next thing I want to check is, do you have NA in the data set? If I run this, it's saying true, there is NA in the data set. So what do I do? Since there is NA, I have to remove. The NA must be removed. So you have to use NA.omit to remove that. We have removed the, okay, let us now try the same code. NA is .NA. You can see this one is false. The first one was true, meaning that we have NA. The second one is now false, meaning that there's no more NA, meaning that we have removed all the NA. We have all the NA has been omitted. So let us now look at the dimension of the first one, the main data set. You can see the dimension. We have 29,101 by 13 variables, by 13 columns. While the clean data set is 25,699. The number of variables are still the same, but the number of observations has reduced. I wrote this code to know the length of the initial. If you want to use length, you have to pick a particular variable. That's why I'm picking pickups, which I'm using as my dependent variable. I want to look at the length and also N for the new data set. I want to look at the length. Then I say omit.data is my own variable name. I'm saying N1 minus N. I want to see how many observations are being omitted. If I print this, it's showing me that I've omitted 3,402 observations. I have omitted 3,402 observations. So,
are you please repeat from the dimension? Take it one by one, please.
Okay. let's look at these parts. Let me do this.
Exactly.
Length of variable. I want to look at a particular variable, the length. You know, I said before that in a table, if column A has 20 lengths, it means that column B2 has 20 lengths, column C has 20 lengths. They should have equal lengths. Otherwise, if you want to predict or do anything, we tell you that the lengths are not equal. So if you look at the length, you don't look at the length of a table, you look at the length of a variable. So that's why I use N1, length of data 1 pickups. The pickups is actually one of the variables we have. So I want to look at the length, but I'm taking it from data 1. Then there is other length I want to calculate, which is N. I call the first one N1, the second one N. I want to calculate the same thing, but now from the second data set, the clean data set. Data one is the data set with NA. Data 1 has NA. Data without 1 has no NA. I can see it is clean. It's clean. So if I run the first one, run the second one, so I have N1 and N. So the difference between N1 and N gives me the number of omitted data, which is 3,402, which is out of 29,101 data. If we take away 3,402, what will be left is 25,699. So meaning that I have removed 3,402 observations from that Uber data set. So the data set I'll be working with now is not data 1, but data. So I think we've gotten this part. Let me copy the other part of it. So want to look
What you are
at,
saying, sir, what you are saying is this particular section can work for any data set.
yes, it can work for any data set.
Okay.
It can work for any data set. Irrespective of the data set, they can work for any data set. Either it's employee data, you have your institution data, your organization data. Once there is no data, a missing value, it is NA. I will see it as NA, meaning that there is no data set, there is no data for that particular cell, which is to see it as NA. If I run this N data 1, okay, let's see. You can see N data 1. Look at temperature for the second observation. Temperature for the second observation. If you look at temperature for the second observation, it's showing that there is NA. We have NA. Let me increase. I want to use my system volume so that I can charge my phone. Can you hear me now?
Yes.
Okay, let me share this thing again.
Are you there, sir?
Oh, sorry. I know
Okay.
it was muted.
Yeah, go ahead now. We can hear you.
Can you see the screen?
Yeah.
The screen is on, Abi.
Yes, it's okay. We can see.
So what I'm trying to explain is, if you look at the first data set, the first data set is what I have here, Air data 1. Air data 1 will show us the first 6 observations. Out of the first 6 observations we have here, if you look at the second row, under the column of temperature, we have NA. We have NA. My battery is low. Let me look for a way to charge this system. No, that is my phone. My phone is what I'm using to do my.
Let's just hold on for our instructor. So at this point now, all we are just trying to expose ourselves to is, how do you handle missing data? In case you are given, remember we are using the industry data now, of which that was one of the things we are exposed to last class. So in this case now, we're using a Uber data set, and from there, we can see when you have the NA, we can see how we can remove the NA, and so on. I think we can try and download as many data on Kaggle. You can download as many data sets, and from then we can use it to be able to use the code. Just all we need to do is just to replace the data sets. And from then we'll be able to have access to as many opportunities as possible. They asked you. So while we're waiting for him, for those of us that have the code, we can continue to check the code, and from there we can try and see the string data, the pair of data, and all pair in the unique way. So while we are waiting for him, so in case you have any question, please don't hesitate to type it on the chat button there, or you can raise up your hand, then we can call, and from then we can proceed if you have any question. Ogunsanya, are you still there?
I'm with you, sir.
Oh, okay. So while we are waiting for him, do you have anything to share with us, sir?
If you, I just want to probably re-echo because what you are looking at now is a real life data. And not found. Okay, we'll talk about that when I check for mine. Okay, somebody is asking a question that I could not find is data 1. Okay, maybe you have not properly called the data from your where that data is actually residing. I also perceive that a lot of us are likely to have problems calling data, reading data from when you are trying to set your directory. Okay, so if it's actually giving you a problem, go back to the link from the folder. So you go through your C. From your C, if you are using HP, go to HP or user. Just look at the path, copy that path and place it in the same place, it will automatically say it. So you don't necessarily need to set that directory if you are actually having problems with it. I don't know if you understand what I'm saying. Okay, I'm not, the screen is stiff now, so I wouldn't, so what I'm saying is that you can use the part of where that data is saved, copy it, change the backslide to front slash. Okay, just change the slash, okay, it's front, change it to back. And then the data, it will automatically see it with that. Okay, so if you're actually having problems with the directory. Okay, so I want to go back. I don't know if Ekum is back. Okay, I want us to understand the question so that we can follow through. For those of us that have the slide, the question we are solving, is important we understand the question. Okay, so the first question says that what are the different variables that influence the number of pickups? So we want to, our pickup is our target variable, which is, in other words, we call it the dependent variable. So out of all the variables, which are the independent variables, which we want to extract based on this analysis, so we want to know which of them actually will influence the number of pickups from different areas, and which areas has the highest pickups, so that they can put more, set more vehicles into that direction. So if we discover that Ikeja had higher frequency, then that means that we should pull out the vehicle from Ikorodu and send them to Ikeja. So we want to really get this information based on data, not we are envisaging because a crowd is in this particular direction, but we want to do this analysis based on the information that are given to us. Which factor affect the number of pickups the most? Okay, is it the weather? Is it time? What time of the day that affects pickup? At what period do we have high traffic? If you check, even those of us that we use all of these Uber, bus, all of these vehicles, I don't know what we call them generally, we discover that the same location, the same distance, but at a particular time, the price is likely to be different. Why? It is driven by this analysis, this analytics that some of these companies use. Because when the traffic is high, they feel that the number of vehicles is limited, then they should maximize the margin at that particular time because of the shortage of the vehicle, and there is need for people to go towards that direction. But when the traffic is a bit light, okay, the price will be attractive, trying to force you to use the vehicle, because at that moment the vehicle is laying fallow, it's not doing anything. So the best they can do is to reduce the price, attract people. So we want to do all of this using, and so that we can advise the management on the fluctuations of the effect of all of these things, and make some decisions. At what time do we release vehicle? How many drivers do we get to get all of this? So it's a complete work, which it is expected that data scientists can assist any organization to make a proper projection. And based on this analysis, I think our facilitator decided to pick regression to solve these problems. You could pick any other problems, any other solutions to solve this particular problem. And that is where, but for those of us that do competitions, we try to optimize, you look at the best model to solve this particular problem. So, but for the purpose of this lecture, I think we are adopting regression to solve it. I don't know if our tutor is back. Hello, sir.
Unmute yourself, please.
Yeah. Hello, what happened to? Okay, I don't know if I should go ahead and share my screen.
Can you please share your screen, Gusaya?
I'm trying to look for it because okay. Okay, I don't know where are we from. Okay, for the person that is complaining of the data, when you are reading that data, see what I did here. Okay, so I'm not setting directory. So I'm using a path to call my data, to read my data. Okay, so I don't know if, at least for the purpose of this class, so that you can move on with us, then we will look at how to go back and beginning to teach ourselves to set directory. So if you are having issues, just go back to the folder where that data is, check that edit, highlight it and copy that part. Come and paste it here, then change that slash, okay, to backward slash. Then it will read the data automatically. So you might not necessarily need to set the directory.
Okay.
Hello.
Hello. I hope they know how to copy the part.
Okay. Is anybody having issues to copy and paste? Just let us know so that we can look at it together. Hello, is my screen?
Yeah, your screen is okay. Try and run the code if possible. You can install other packages, then run it. Let's continue while we are waiting for Ecom. You can continue from where you stop.
Okay. Okay, so we just assume that there's no problem till
33.
33. Okay, so
Yes.
he was trying to show us here. Was trying to show us. Let me try to.
Hello. Hello,
Okay.
Dr. Musa.
All right, sir.
Hello.
Thank you.
I'm on now.
All right.
Okay. Sorry for the.
So you can share your screen, Ecom.
Okay. Thank you, sir. Sorry, my system went off. I was trying to connect it, went off, and NEPA also took their light. So
It's okay. It's okay. Don't worry.
Okay, we know you are in Nigeria. Go ahead.
Yes, thank you. So we have done this. Let me okay. Okay, I think I've done all this.
In the edge, yes.
Yes, this is the head.
Yes.
Head one. Head one, if you look at the second row, there is NA, meaning that there is a missing data for this temperature. For this second set of observation, we have NA, meaning that there is missing value there. That's why I will return NA. But if I run the edge for the next, for the clean data, which that is the one I named data, you can see that second observation has been omitted. Look at the first row here. The second row is omitted. The third one is there. The fourth is there. The fifth is there. Sixth is there. The eighth is there. Arrow will not renumber it to show you that all these things are indexed, meaning that all the rows are unique, as I've earlier explained. So it has only removed the second row from the data set. But if I show you all the data set, there are a total of is it not 3,000 we saw the other time? 3,402 observations that was omitted. The first one that was omitted there is the second row, and many other rows too, making up to 3,402. So let me go and copy other parts of the code so that we can also execute them. Let me copy from the data description. I think maybe Dr. Guza have explained part of that, but let me just copy it to, this part. I will explain the code one after the other. So I have copied the code. You already have all the code, but I'm just trying to copy it. And okay, I stopped here. Let me put double. All these are comments. We execute. I'm just trying to separate the top part from the second part. Now I want to look at the data description, though it's already on our PowerPoint. In case you don't have that PowerPoint or the slide, you can see the data here. The data contains the details of the Uber rides across various boroughs subdivisions. So those boroughs are subdivisions. We have subdivisions under borough. Then we have the variable name and the description of the variable names, which we have also seen in our PDF. I will skip all that, but in case you don't have the PDF, you can easily go back and look at this. The temp is the temperature in Fahrenheit, and dew is the dew point in Fahrenheit as well. So all these variables are already explained on the slide. So now, as I said before, if you want to look at the description of the data, I'm talking of the clean data now, just run this. You can see the data.frame, that what you are running is actually data.frame, which is a table. If it's in Excel, you call it a table, but in R, we call it data.frame. So we have 25,699 observations of 13 variables. So the variables are pick-up dates, the borough, the pick-up, the speed. If you count all this, there are 13 in numbers. And the first one, which is the pick-up date, is character. The borough is also character. The pickup, number of pickups, they are integer. Number of pickups, if you have no pickup, that is 0. It's not NA. 0 is not the same thing as NA. It means that that particular period in time, there is no pickup. Then we have the speed is also the wind speed in miles per hour. This number means it's continuous. You can have decimal. That is the meaning. But once it is integer, it means that you cannot have a decimal. So we have the first one, which is the pickup at the dependent variable, and every other thing there as the independent variable. So let's continue running the code. Then PS, let me reduce this to the first, the 3 to 5th row columns. The third column is what? We have the pickups, that is the dependent variables on the third column. The fourth column, we have the wind speed, and the fifth column, we have the visibility. If I run this code, it will just give me pairs of 3 variables. Let me run it. It's sometimes take time to produce output. So just exercise patience to produce output. Can you see it? We have the pickups, we have the we have the wind speed, and we have the visibility in miles. So we just have these 3 variables. And these are the scatter plot and plot. The scatter plot between pickups and wind speed is this first one. The scatter plot between pickups and visibility is this second one. So I can have as many as this plot as possible. Only that it will take time, but let me see if I put up to 8. I can do it up to 12. Only that it does take time to be executed. I have run this. It will take time. Everything will come out.
Please, can I ask a question? Does it mean
Okay.
anytime we put the PS, we are talking about scatter plots?
You are talking about scatter plots.
Okay.
But in matrix form.
In matrix form. Please put the comment there in your code.
Okay, let me put the comment. So just like your correlation plots, but the correlation plots will give you values, while the PS will give you the scatter plot. So it's also a form of EDA. It's also a form of EDA. So that is what that will give you. So because I put in 3 column 12, it's taking time to produce the plots. But if your system is very powerful system, it will produce the plots quickly. But if your system is not that powerful, the code is somehow slow. It takes time to produce the code. Maybe if you are a good programmer, you can produce PS that will run at a quick time to produce the results, a faster time to produce the result. But let's just wait for the result to come up. Then to be produced.
So some of us have the results.
Okay, some already have the results.
Yes.
For 3 column 12.
Yes.
Okay.
That is using better machine.
You say? And those people that are using better machine already have the result for 3 column 12. Mine has not shown, but I don't think any other thing will be able to be executed without that, because I need to explain other lines too. People using better machine have already seen their results. You know, there are some codes that can take time to be executed. You can travel and come back and see meet your machine running. But this will not be as long as that, because I've done it before. That was why I reduced it to 3 column 5, so that I can easily see the results. But I still want us to see 3 column 12. You can only take 3 column, but we have the maximum of 12 variable here. The 13 variable is the okay. My result is out. Thank God. My result is out. Yes. So we can see all the variables. I pick from the first variable that is numeric to the last variable that is numeric. I didn't pick variable 1 and 2 because they are not numeric, and I didn't pick variable 13 because it's not numeric as well. So, but these are the numeric variables. You can see all the scatter plots, and you can see the ones that are positively correlated, negative correlated, no correlation. They are all there. They can export the plot, save as image, you can save as PDF, or you can copy it to the clipboard and paste it. If you are using Word, just copy to clipboard and paste it to where you want to paste. But if you are using latex, you can save it as image or as PDF. Then you attach it to wherever I want to attach it to. Then the next thing you want to look at is all pairs. All pairs will just bring all the data points for if I run this lens, it's showing that we have 6. This borough, or what I call the subdivisions. What do we call it here? We call it yes, subdivisions. We call it subdivisions here. So it means that we have 6 subdivisions. We have 6 subdivisions. So that's why it's giving us 6. So the length of all pairs there is what? 6. If I use gender, I didn't mean that it's a gender data. The length of all pairs will be what? 2 for male and female. But in this case, the length of all pairs is, let me see if table can produce what I need. Maybe let's see table. If I table this, if I table this, if I table this, yes, table has shown me the result of what I want. So we have 6. You can also type down tables there. This function, table of this, it has given me the 6 and showing me the count. For bronze, I have 4,343 observations. For Brooklyn, I have 3,984 observations. For EWR, I have 4,343 observations. For Manhattan, I have 4,343 observations. For Queens, and so on, and starting island. So we have 1, 2, 3, 4, 5, 6. So I have 6 subdivisions in that particular location. So that is what that table has helped me to do. So if I run this sample pair, the sample pair just show me all the variable names, but the table did not show me all the variable names only, but also shows me the counts. Then what I want to do here, let me put comments here. I want to split this data into 6. Split the data into 6 subsets. So I'm splitting the data into 6 subsets. The first subset is named data.starting island. I cannot put island there except I put .island. Then the second is data.wewr. The third one is data.brooklyn. Fourth one is data.bronx. We have data.queens, and we have data.manhattan. It's the same code for everything. Is this subset we use? The data here is that my data name. I don't know what you have named your data, but my own data, I just name it as data. Then the column name, or what I call the variable name, is borough. I have put in starting island. What this place is saying that from this data, where this borough is starting island. If it's Nigeria, we can see maybe from this data where LCDA or where LGA is this particular stating island. If this gender, you say from this particular data where gender is male. You now do another one for this particular data where gender is what? Female. This code can run for any, this subset can run for any data you want it to run for. But for these ones, we have 1, 2, 3, 4, 5, 6. We have 6 subdivisions and we have their names. So once you do this, it means that we have all these data sets. We can run the regression on the entire data set, and we can decide to run the regression on individual data set, individual subsets. Then if I do, for example, the first one is head data.queens. Let me run this one first, because if I run this one, it will give me error. It means that I'm supposed to run these ones first. Yes, I can now do the head of data.queens. You can see everything I have here under borrowed and what queens. If I show all the values, let me just run this one alone without putting the head, so that you see what I'm saying. If I print this data alone and see everything there, everything here is queens. You can see all through, you just see queens all through. Can you see that? Okay, but you don't need to see all the data sets. So that's why I just need to run the head data.queens, so that we just see the first 6 observations. The first observation that is queens is observation 5. Then the second one is observation 12. The next one is observation 19, and so on. So you have selected all the observations where borrow is equal to queens. Then we can look at the length. How many are they? How many observations do you have? You can see that we have 4,343. If you go back to that table we did the other time, let me run the table again. You can see that queens is 4,343. You can see that we have the same value. Okay, let us go further. If we want to run multiple plots on the same canvas, on the same page, you have to use this per mf row C2, 3. It means that the first one is row and the second one is column in that order. It's an ordered set. So the first one is 2 rows.
Please
the second
put
one
the
is 3
comments, sir.
columns. Okay, let me put the comments. So this line is used to run multiple plots on the same page. Let me continue with this. So C2, 3 means 2 rows and 3 columns. Okay, so let me run this. So if I run the first one, the first plot is occupying the first row, first column. Second plot is occupying the first row, second column. Third plot is occupying the first row, third column. Then the next one, second row, first column, second row, second column, and second row, third columns. So these are all the plots. They are time plots for each of those subdivisions. So I decided to run everything so that I can see the plots for the number of pickups. The number of pickups for queens is, can see that it's increasing. So though it's fluctuating But if you look at it in the long run, it is what increasing. That of Brooklyn 2 is also increasing. For Bronze 2 is also increasing. For some of them, it's not showing if it is increasing or not. But at least for these three, they are what increasing. You can see from the plots. Then I can also run the histogram to see the distribution. This one is skewed. For starting, is very skewed. This one is highly skewed. This one is also skewed, but at least it's showing some little normality and little bit level of normality. This one is also skewed. This is skewed, but at least it's showing normality to some high level. Why this is skewed? Meaning that this variable as a whole cannot be used. We cannot use linear model. But in this study, I'm using linear model just for practice sake. But actually, if you want to look at this variable, it has a particular distribution it follows. It can be gamma, it can be Weibull. So instead of using LM, we can use GLM to achieve that. But for today, it's just LM. But the difference between LM and GLM is just the G before the LM. Then you tell us the distribution, the probability. Maybe it is gamma. If it is or Gaussian, if it is Gaussian, Gaussian is same thing as your normal linear model. It can be gamma, it can be other ones. So we have the mean. You can calculate the mean of this particular data.queen. Now I'm not I want to concentrate on data.queens. If I run this, this will give you the mean. This will give you the standard deviation. But instead of just typing mean to get this or this to get this, I can just click on the summary. The summary will give you the mean, the first quartile, the median, the third quartile, the minimum, the first quartile, median, mean, third quartile, and the maximum. If I use 5 norm, if I don't want to use summary, if I use 5 norm, if I change this one to 5 norm, 5 norm, 5 norm will give me the minimum, the first quartile, the median, the third quartile, and the maximum. So that is the 5 norm. Those 5 norm are what we use in plotting our box plots. Let's assume we want to plot box plot for this. If we put box plots, though these are not part of what I'm running, but if I just want to see the box plots, you see that it will be inch on those values. If I run it, you can see the box plots. The minimum is 0. The first quarter is 196. The median is the tick value that is dividing the box. The tick line that is dividing the box, which is 308. The third quarter is just above the tick line, which is 410. And the maximum value is around 831. This one is showing outliers, that we have some outliers in the data set. So we can also do data.queen to show the one that has the minimum value. The observation that have the minimum value to show you the rows, the particular observation that have the minimum value. So let's go and pick the next set of codes. Okay.
They ask a question, how can we show the distribution of a particular data set?
How can you show a particular data set? It's from
Yes.
the histogram. The histogram will show you the distribution, the shape, but you yourself must have known each distribution, how they behave. If you see a normal distribution, by now all of us know that a normal distribution is symmetric. you see the histogram that is normally it is evenly spread. The mean median mode will fall at the middle point and it will spread down. You know that this is normal distribution. If we see exponential, you will see it. If you see gamma, you will see it. Weibull, it will go and go up and later come down. So if
Hello,
you know
sir.
the pattern
Hello, sir.
of those, yes.
When we see all those, what you are saying, we don't know it. That's why they asked the question. So
Yes.
our advice, if you have example now, fine. If you don't have, probably next class, if possible, you can show
There's
us.
no example here, and there is no way you can know that a distribution follow a particular, that the data follow a particular distribution, except you test that distribution with the data. Just the way we test for normality, you have to test the distribution and the data to see if the distribution actually fits the data. Do you get it now?
No,
you have to do a test to do that.
That's what we are saying. Are we doing the test now?
I don't have that here.
Okay. Probably next time we can have a text on a particular data set that will help us.
Just like what your Guru Sinop will do, your KS test. Your KS test can actually look at the data set and the distribution you are looking at, if it follows it. And you have to do it. You look at gamma, you look at Weibull separately, you look at normal separately, and it will give you, not that you just have a data set and it will not tell you that it follows normal. No, you have to do a test to check if it's normally distributed. We have the Shapiro test. We have many tests for normality that you can easily look up and do it to test for normality. We call them the confirmatory tests. All these histogram, bus plot, and others that are just EDA that will give us idea that, okay, this data is not normally distributed, or the data is normally distributed. When we do our Shapiro tests, or we do our many other, like your KS tests, it will give you the test statistics, also give you the p-value. So the p-value will tell you if the test is actually normally distributed, if the data is actually normally distributed or not, or if the data actually follow gamma or not, or if the data actually follow that particular distribution you are trying to test it with or not. So those are confirmatory tests. It's not part of this code. I can provide the code later.
Thank
but just
you.
Go, so you can just search for KS test. It will show you that. You can search for Shapiro test. It can show you that. So for the next thing we want to look at is the ggplots. It has jumped the ggplots to the, let me do the ggplot first before I go to the correct ground. Okay, this one is taking time to show.
Data is large.
The data is large, yes. So it has given me the results. This is showing the scatter plots of pickups and temperature. Pickups is my dependent variable, temperature is my independent variable. But I'm now looking at it from different localities, different points. This size 2 here is the size of this box. The alpha is the initial size. For some system, it will be showing you as it's loading and progressing from the first data to the last data. It will show the progression. But this is the final results. The colors shows the different locations, and it's like this particular Matama is the one that is most here. Some of them have been covered. So it shows the different spread, the different distribution, how they are related based on the pickups and temperature. Then the next one we want to look at is the correlation graph. If we look at this, it will show us this also a correlation plot like the one we did before. we have the pickups, we have all the independent variables. So if you look at the pickups with all the independent variables, showing that most of them have weak correlation with pickups. The ones that have high correlations are between temperature and dew point. If you want to use temperature to predict dew point or use dew point to predict temperature, you can see that the correlation there is 0.9, meaning that they are highly correlated. Others have low correlation. This one is temperature, and these have negative correlation, which is a bit high. So this can also go in for your peers. If you don't want to use your peers that we used before, we can use this cogram. You can also use it to represent your correlation matrix. Instead of having your correlation matrix, this can also go for it. And the color shade also shows the correlation. Not if you don't want to use the colors, but the values are there, so you can easily see the values. Then at this point, I want to go to the, maybe I should type here, and splitting data into training and test, into train and test sets. Into training and test sets. So if I run this this set or seed, so that if I do the random, it's a random way of generating values. So that if I put it set.seed, if I do it many times, it will still be repeating the same result. If I not set seed, the result might differ. The sample set is going to select will differ. Imagine you want to do your PhD presentation and you already have a particular set of results, and you now get to where you want to present it, you run it again, you get a different set of results. So what we use the set.seed for is that if we are producing these random numbers, produce the same set of random numbers. That means I fix the random numbers it will produce. If I run it many times, you still be producing the same set of random numbers. That is the meaning of set.seed. But if not put set.seed, each time we run a random number, each time we generate a random number, different set of random numbers will be what? Generated. So that's just the purpose of the set.seed. So let me run it again. Then add data. Now, I want to reduce my data from column 3 to column 12. I don't need column 13. I don't need column 1 and 2 for my linear model I want to run. So I want to base my analysis, my model on column 3 to column 12. Column 3 is my dependent variable, while column 4 to 12 are my independent variable. So I now have data 2. So if I add data 2, you can see I have my pickups, I have my visibility, temperature, dew point, and so on. So these are my, from this point to this point, are my independent variables, while the pickups is my dependent variable. In this new data I have now, there's no pickup dates, there's no borrow, there's no holiday. So I only have the numeric data. Now, I still want to put that data 2 back to data, so that instead of me using data 2, I will keep on using data. So I have assigned back my data 2 to data. It's not compulsory. If you don't want to do that, you just keep on using your data 2. So, but I've assigned my data 2 to data, so I keep on using data. Now, sample splits. The keyword here is sample splits. that split this data into 2 in the ratio 0.7. Once you put 0.7, the system knows that the next one is 0.3. The other part is 0.3. So if I run this, it's giving me 2 data sets. It's giving me 2 sets of values. One is true and the other one is what? False. Let me quickly do something. Let me try table. Let me put this sample splits. Let me see what I'm going to have there. Okay. As expected, I have false, I have true. False is 7,513 and true is 18,186. So I split the data into 2. 7,513, that is the 30%, and the remaining 70% is 18,186. So I now assign the larger portion, which is true, to train data sets. Why I'll now use the remaining 30% as test data set. So if you look at the code, I use that subset, my data sample split true, and I use the remaining one, which is false, as my test data. So let me run this. Okay. Now, my first model, model 1, I just want a simple linear model.
So there is a question here, sir.
Okay.
Please, will the split be done orderly or randomly?
Randomly. The 70% and 30% has been done, but the data that will be included in the train set will be selected randomly. Not that you pick the first 70% for training set and now use the remaining 30% for the test sets. What it will do is that it will pick 70% from all the data sets. You can pick the first one, pick the third one, pick the 10th one, pick the 15th one, but it will pick 70% of the data sets for the train set. You now use the remaining one for the test sets. So that is the idea of it, because this more or less as statistics, it's like you are doing random selection. You want to select 7 people out of 10 people. You don't just select the first 7 or the last 7. You randomly select 7. You get it now? So the system will randomly select 7. That's why we are setting seed that if you are selected, for example, we have 10 observations and you want to select 7. What that set does seed is saying that if you select first observation, second, 5th, 7, 8, 9, 10. Each time I run it, those are the sets you should also keep on selecting. That's why the set of seed is there. You get now, if the set of seed is not there, each time I run it, I will get different results because it will pick on that 7 observation differently. So that's why you should set the seed. So the observations are picked randomly by the system. So let me run the first model. Model 1 is LM, which is linear model. I have my formula. I have picks of this sim. This sign here, we call it sim, or I don't know the symbol you want to call it, but I always call it sim. But you can always see it at the top of the tab when you hold your shift button. If you hold the shift button and press that, you will see that symbol there, a sim. Then temp is the independent variable. You know, pickups is the dependent variable, while temp is the independent variable. Which data am I using? I'm using my train sets. Now I've divided data into 2. I have to train some sets. Then I'll use the other set for testing, for test. So 70% of it is going for the training, while the remaining 30% is going for test. So if I run this, I have done my linear model. I have done my linear model. Then If I want to look at the summary of the linear model, that is the next line. This is the summary of the linear model. From the summary, I can get my residual standard error, the degrees of freedom, the multiple R squared, that is the question of determination. I can get the adjusted R squared. I can get the F statistics for the model. 1 degree of freedom by 184 degrees of freedom. One by, it should have the numerator and the denominator because F, they have the P value for the model. The model is actually showing that it is significant, meaning that it can be used for prediction. But the R square is telling me that, hey, you only have 0.4% that can be explained by the independent variable, which is not a good one. But the p-value for the intercepts is showing that it's significantly different from 0, and that of temperature is for the coefficient for the slope. It's also showing that it's significantly different from 0. So there is this what Prof told us the other time. Let's look at it. Plot model 1. If you run this plot model 1, it's supposed to give us a plot. Okay, this is the residual versus fit plots. This is normal QQ plots. This is scale location plots, and this is the residual versus leverage plots. If you look at this, you discover that the error itself is not normally distributed, meaning that the values you are getting from here, this beta, it cannot be relied on because the data itself, the dependent variable is not normally distributed. So we are only forcing normal on it. But some people will not mind, they will just go ahead to use it for prediction. Why people in statistics, these are part of why a statistician is different from somebody in machine learning. Somebody, a data scientist, we only look at the predictive power of that model. You might not necessarily look at all these diagnostic tests. We call them diagnostic tests. But as statistician, we look at the diagnostic tests. We say, this is not a good fit. So I also look at another model. Okay, let me look at this GG.
Sorry, there's a question here.
Okay.
You have model 1 and model 2.
Yes.
And I can see the training set for both of them.
Yes.
Is there anything different between them?
Okay. Let's look at model 2. Model 1 is, let me just put comments here. It's a simple linear model. That one is simple linear model. The second one is multiple. The second one is multiple linear model. Both the simple linear model and multiple linear model have the same assumption. The only difference is that the multiple linear model, we have more independent variables than the simple linear model. And once you have many independent variables, we expect that the number of observations should be more than the number of independent variables. And the issue of multicollinearity can also set in for multiple linear regression. I think now those are the differences here. For simple linear regression, there is nothing like multicollinearity because it's only one variable you are looking at. For multiple linear regression, you talk of multicollinearity because if one variable is doing the same thing with another variable, if it's a factor or a multiple of another variable, you end up your S prime S, your design matrix will not form. It means that in mathematics, we say they are linearly dependent. And once they are linearly dependent, the determinant will be equal to 0. And it cannot be invertible. That means that matrix will not be invertible anymore. So that is the difference between simple and multiple linear. Another thing about multiple linear is that For example, like what you have here, you have 12 independent variables, 11 independent variables. You now have 10 observations, then your design matrix will not form because you are saying that your degrees of freedom is less than the numbers of variables you have. So it will not form. So that means for you to use a multiple linear regression, your number of observation must be far more than your, in fact, 2 times more than the, at least 2 times more than the number of variables you have. But for simple linear regression, I don't think that one occurs because definitely you have more than 2 observations to run your linear model. Both simple and multiple are still linear models. Only that one has one independent variable and the other have many independent variables. Then let me run the second. Then if you look at the code here I'm just using temperature as the independent variable. In this place, I've used option of temperature plus SDP plus, I can be adding all the independent variables. I can have 10 independent variables. I add them with plus, like what we did in the other last week. We can add them, but a simple way of doing it is just to put dots. The dots there shows that pick every other observation. Pick every other variables other than the pickups. Every other variable in that data set, pick it as independent other than pickup. Meanwhile, this data we have now, we have removed the dates, we have removed the variable, we have removed the holiday, all those ones, they are not numbers, so we have removed them. The new data set we have now have about 12 columns, and all the columns are numbers. So the data, we are still using training data set. The difference is just that this one is only temperature, while this one is all the variables. That's why I just dots. So if I run this, if I do the second model, you can see all the first one is the intercept, this is the constant. Then we have all the independent variables showing. Some of them have positive values, meaning that they are positive related. Some of them have negative values. You have the standard error. The estimates are the unknown parameters that we have estimated. So these are the values of those parameters that we have estimated. But we can't rely on them if the dependent variable itself is not normally distributed. There are many other ways you can look at the dependent variable to normalize it. But maybe after the training, if we have time, we can just discuss that. Then we have the standard error, we have the t value, we have the probability value. The p value here is showing that this one with 3 stars is showing that even at 1% level of significance is still significant. And since we are using 0.05, it means that this one is significant. That is SPD is significant. The VSB is significant. The temp is very significant. The dew point is significant. All these ones are not significant. The PCP is 24 is the precipitation at 24 is significant, and the SD is significant. So we have 1, 2, 3, 4, 5, 6. So we have 6 variables that are significant, and we have the result from the residual, the summary statistics. We have the result here. At least the R squared here is better than the one we had before with 1 independent variable. Though it's still not good, but it's better than what we have before. But if we normalize that dependent variable, you discover that the result we get will be far better than this. But I did not go to that point because of time. So if we quickly look at the predict, let's look at the predict now. Okay, let me run this. The model 2, the same thing I did for the model 1. Okay, this is the plot for model 1. Let me also do the plot for model 2. Plot model 2. This is not part of the code, but we can just quickly type that and run that for model 2. Let's also see for model 2. Okay. Okay. It's coming gradually. So this is the scale location, this is the residual versus leverage. So you can see that this one is still better than what we had before. Then you also look at the ggplots of the model. Let me run this. The model residuals 2. I want to run from just because of everything I want to do from here, I can do it for model 1 and model 2. But let me just do it for model 2 only. You can replicate it for model 1. If you have more than one model, you can replicate it for this model. The keyword here is as the data frame. I run this, then the ggplots. This is the ggplots. You can see the residual is not normally distributed. So if the dependent variable is not normally distributed, the residual too will not be normally distributed because the residual and the dependent variable, they have the same distribution. From what I see here, this one is even more like Weibo. You can see the first bar here, it went up and it started coming down again. This one is like more of like Weibo. That's why I say if you know those distributions and you see them, their plots, you can easily see this follow. If this exponential, this one that is here will come up and will start coming down like that. That will be exponential. So the sky blue color, if you change the color, this sky blue color, if I change it to all this color, once you know names of color, you can easily do this, change to green.
Can you please explain the interpretation of the graph?
Okay. If you look at these plots, it is the residuals of the model 2. It has calculated the residual. The residual actually means the difference between the actual values or what I call the observed values and the predicted value. You know, when I showed you the Y the other time, the model the other time from the PDF, we have the actual values, the actual Y, which has the error term. By the time we estimated the unknown parameters, we have under Y, the second Y has Y cap, meaning that the new Y is predicted Y. So the difference between the observed Y and the predicted Y is the error, or what you call the residual. Most time we call the error when we use the population. Residual is the actual result that we get. So when you plot the residual, this is the histogram of the residual. This is the shape of the histogram. So we use ggplot. This particular code will not run if you do not call that library ggplot library. This one will not run. So this one is running because you already have that library installed. That's why this is running. Then the histogram, the field is saying that the color, what is the color you want to give to it? So if you know color name, let me say violet. I know there is a color called violet. Let's see, violet. This is violet. If I run it, it will give me violet. So it depends on the color you want to use. Then the borders are black, so you can easily see the bars. This is histogram. This is not bar chart. This is histogram. Histogram is used for data, for numeric data, continuous data, while bar chart is used for count data. So now let's look at predict model 2 then against this. If I do this, it has actually predicted the values for me. The predict value, I can use the predict value to also do this histogram of the predict value and so on. Then the model evaluation, let me run this. Then the column names. If I do this and run this, to give me the values of all the observations that I have, the actual values and the predicted values. The actual values and the predicted values. Then If I want to calculate the error myself, that I don't want to have the errors, I can just run this. This is the error I mentioned. This is the actual value. And this is the what? Predicted value. Because I've named it that. So actual value and predicted value. And this is the error. If I print the errors, let me see the errors. Let us see it. If I run the errors, which is not necessary, but let me just run it so that we see it. We can see the error values. Ordinarily, the errors are supposed to be zeros or close to zero, or the number of negatives should be equal to the number of positives, so that when you sum it, so that when you do the sum of the errors, so that when you do the sum, if I sum the errors, I expect to have zero if it's normally distributed. If I run this, you can see the sum of error is not giving me zero. It's giving minus 98, minus 983,475. So that is the sum of the error. If I want to square it, I can find this square and sum of square errors by just squaring. I square it before summing it to give us sum of square errors. So anything you want to calculate, once you know the formula, like all those formulas we have in our PDF, we can actually calculate them there. Since you know the errors, you can calculate the sum of, this is sum of the errors. Let me call it SE. Let me call this sum of error SE. Then I can say residual sum square. I can have this one to be SE. No, I can have this one to be, I'll square the error first before I sum it. I can square the errors first before I sum it. I can have this. So once I have this, I can do every other calculation I want to do. I can find the MSC, I can find any other calculations, I can do many other things. But the system has a way of calculating all this without you stressing yourself. Sigma is the standard error, or this you just calculate for model 1. You can, that is the root mean square error. You calculate for model 2. You can see the model 2 has is better than model 1, but I can't say it's that better because model 2 has a lot of independent variables compared to model 1. I just see the two difference between the errors. The mean square error is this. It's just the square of the first one. Just the square of the first one. You can also look at the AIC. The AIC of the, you can now see that the AIC of the second, okay, the AIC of the second model is still smaller than the AIC of the first model. Then use this one for the confidence interval. For each of the parameters estimated, you can actually find the confidence interval, the lower bound and the upper bound for each of the parameters estimated. Then we can also do the correlation plots. We also look for the correlation between the predicted value and the actual value. You can see that the correlation is small. In fact, from the question of determination, you also know that the correlation is small. It's not that significant. Then this, the length of picos. If I do this plot, the plot I'm showing here, I've already shown it from that plot of the model. This is just one of the plots we have from the plot model. Once you plot the model, all these plots will come out, and this is one of them. So I will stop here. The model I have down here, I'm constructing it for maybe for data science. Like what's the model I have down here, I'm not going to run it for now. It's for another level, because you can see end. If I call up this library leaves, I can actually run this regression model, multiple linear regression, stepwise, meaning that it will be adding. I can use forward and I can use backward. So that is what this one stands for. If I want to run this, I must run this library with leaves and begin to run this. But I want to
Please
go
don't
into
run
this
it
now.
yet, yeah?
I'm not going to that now because that if I go into that, I'm going to machine learning fully. But with what we have learned today, we can at least improve our knowledge, look for other materials. At least we have the basis of what we should know. I think from now we can ask questions. We have Prof in the house that can answer questions for us. But let's ask questions first. Then we see how to contribute to the question, to answer the questions.
Thank you so
Mr.
much.
Dr. Kerr can take over.
Thank you so much, Echo.
You're welcome, sir.
We are really grateful for the in-depth. Like we said the other time, this is awesome. I must confess, majority of industry data, when they say clean the data, do these missing data, how do we fill up, how do we eliminate, and some other things. Like you mentioned it, that the diagnostic test, they can easily ask us in our interview, are you applying for biostatistics, statistician, are you a data scientist and some other thing? How do you diagnose a data set? How do you work on this data? How do you clean the data? How do you train the data? So at least we have idea of what to say. So as you can see from the chart, if you know, please can we just, no matter your position, just say a thank you message, send a thank you message on the chat so that we know that you are with us. You are also there. Please just type it. Thank you, and thank you. If you have any question or any contribution, please, let's just raise up our hands on the, and we can unmute ourselves so that we can unmute you and ask question concerning today's presentation and on. If your laptop is there, please do it. If your laptop is not there, please, let's try as much as possible. Let's watch the video. And I believe you can boldly say you can clean the data, you can look at the data, you can diagnose the data set. You can run EDA without any stress. All we need is keep the code, just attach your data set, and that settles it. Any question, please? Any contribution, any addition, subtraction? If you have any question or you want to add one or two lines.
Dr. Adeshina is in the house.
Dr. Adeshina, over to you, sir.
Hello?
We are hearing you, sir.
Yes, so sorry, where I am is a bit noisy. Well, I just want to I encourage you to take this lecture seriously, because it is going to be a plus to you. And whatever it is that is not clear, you can as well reach out to any of us, particularly this area of machine learning, training, and testing of the data set. There are a lot more to learn about it. So feel free to get back to us, to ask us questions, and we'll be willing to give you answers. That's just it. So I believe what you have learned tonight, if you are to learn it on your own, it will take you weeks, if not months, you know. So just take advantage of it, go over the notes and the lecture materials. And I know that if you diligently look into all these things, you will find them easy to play around with. And I believe if you put your mind there, the sky is the beginning. Thank you. Thank you to our facilitator. God bless you.
Thank you, sir. Thank you, sir. Okay, do we have any question again? Contribution, any question?
Good.
Okay. So what we are saying is let's try as much as possible. Ekum, you promised us
Yeah.
something about normality. Can you
Yes,
share
sir.
more light on that before we
Okay.
just
Okay.
say what are the things we should be expecting on that? Just to collaborate.
Most of, if you do your box plots, your QQ plots, your histogram, all those plots, they are preliminary plots, they are preliminary analysis. We call them EDA. You can actually see from there if your dependent variable is normal, if your data is normally distributed or not. If your number is not data is not normally distributed, you know that it follows other distribution. For the linear models, one of the assumptions is that your dependent variable must be normally distributed. So we have many options of confirming that without the plots, because sometimes the plots, if you don't have an eagle eye to know that if it is normally distributed, in fact, if you don't know normal plots, you might not see. If you don't know that the normal distribution, the histogram, how it looks like, you might not know if the data is normally distributed. So confirmatory tests are many. You have the Shapiro test, you have the KS, that's Kolmogorov and Smirnov test, and many other tests. So if you just like KS or test, and you put the variable and the data and the normality and normal distribution, it will show you if it is normally distributed or not. You can use a Shapiro test. There are some packages that when you put it, you can do all the tests for you at a time for that particular observation or for set of observations. It will show you all the results. It now depends on you. When you see a p-value, you're able to know how to interpret it. That's why you must know the statistics. What is the null hypothesis saying? What is the alternative hypothesis saying? If you know what the null hypothesis is saying, null hypothesis might tell you that the distribution is a good fit, and the alternative might tell you the distribution is not a good fit, depending on each test you are doing has its own null and alternative hypothesis. So once you know the null and alternative hypothesis of a particular test, then your p-value cannot tell you if that test, if that data is normally distributed or not. Then also, if it is for gamma, you must also know how to use like KS and test, the Smirnov test can go for any distribution. Yours is just to know how to generate that particular distribution. You now compare with the data sets. You know, it's from the data set you will generate the parameter for the distribution, and you compare the actual data and the theoretical data, which is from the distribution, and it will tell you if the distance between them, if the Euclidean distance that you have calculated, if they are close, meaning that it's a good fit, and they are not close, meaning that it's not a good fit. So all these are things you can learn on your own. Just go online. Like with that in distribution is what we do almost all the time. When you have a data, you have developed your distribution. You want to see a data that can fit well to your distribution. We start looking for data that looks like our distribution. And once it fits well to our distribution, better than any other distribution, we turn it to a paper. We say we have a distribution that can fit this particular data set and related data set. Before you know it, it becomes a paper. So that's what we do. So just look for, you can go online and search for, but for now, just look for a way to know if the data is normally distributed or not. There are many ways you can normalize it. You can easily write a simple code, the maximum minus the value over maximum minus minimum. It will normalize it immediately. But the problem here is that most people, they normalize with a particular code. They don't know how to return back to the original observation. That's where the danger is. So if you are normalizing, for example, if you are using log, your dependent variable, you are logging it to run your analysis, your final answer, you must be able to do the exponential of that value to return it back. So all these are things you begin to learn as you are working on predictive model. Like then for the linear model, to try to generalize linear model, just put GLM. You now look for the type, maybe it is gamma or Gaussian or binomial, binom for binomial or for which other. Just type GLM in your type GLM, FGLM or question mark, double question mark GLM. It will give you everything you need, or just go online. Google is our friend. Once you just go online and just type what you want, Google will give you a lot of results. Or just go to Kaggle. Try to be join it. You get anything you want to get, you always get it online.
Thank you so
It is
much,
not left
sir.
with you now to interpret your codes and adapt it. I think that is sufficient. If there are other profs, other doctor in that. Mr. Augusta, is Augusta there?
I'm
Dr. Augusta. So you can also throw light, because next week, most of these things
What
you have
light?
to.
Okay. All right.
No, it's okay. I think you have explained it, but most especially, I think what we are trying to say is that anytime you are using a linear regression, there is an underlying assumption, and the assumption is normal distribution. So if the data does not follow normal distribution, what else do I do as a data analyst? So I need to normalize it. So he said, for the purpose of this class, we are not going to that section. Okay, but we are just trying to see how we can use some of the things that we have learned in the last 3 weeks, use them at least to this level. So another level of, trying to work on data, do some predictive. Some of us are actually running away from statistics. If you want to really do more, perform very well in this field that the world is tending towards, we need to go back to statistics, mathematics. They are crucial. They are too important to be neglected in this area, most especially if you want to adopt R. For those of us that would like Python, and maybe we can dodge some of these statistics, because some of those packages are available. We just adopt them and we go our way. But R, we just need to be grounded in statistics. And I think he has explained little of it, but because of time, we can't do distribution, because Ecom is taking you into distribution because that's his own area. Okay, please, this lecture is not only for distribution, it's actually for R. But it's also very important what he has mentioned. So please let us know, for every statistics we use, there is an underlying assumption. And we must know those assumptions for us to use them. So it is not because Ecom has used it now, it might not be okay for your own set of data. Okay, so we need to know how our data look like, how is it behaving, the trend, the pattern, then before we adopt the kind of method we use to solve the problem. Thank you. I think that's my own contribution. So hopefully we're getting ourselves ready for another series. We're heading our series today. We are picking up from where it stopped from Python. So let us also get ourselves ready, download all the downloadables in Python, and let us get ready for next week lecture. Back to Dr. Okay.
Okay, thank you so much, sir. Thank you so much, Ma. Can we do a futures schedule for? Okay, we'll work on that.
We'll put that in the platform, sir.
Okay, thank you so much, everyone. God bless you all, and let's see next week.